So this week we'll probably finish chapter 7. We skip chapter 8 and then go into chapter 9. And a reminder about exam 2, we're going to do that next week. We'll do a review next week. And I want to let you know about your homework, actually. So you have homework due on Saturday. Seven 1 and 7-2 are both due this Saturday. And let's just go ahead and say that the test, the second exam, will go from where we left off from the first exam up to 7.2. Okay. Hey, everybody. We are making it through the notes. Happy Wednesday. Okay, so I'm going to go ahead and start the next section, which would be 7.6. I think this is going to be pretty cool, and I want to do more examples Friday. Improper integrals. So there are two kinds. Okay. The first type 1, could happen in 3 different ways. So the first way, we'll call part A, is the integral from negative infinity to b of f of x dx. And wish I had a bigger whiteboard, kind of working towards a better setup actually, but we'll see. Okay, so different kinds of improper integrals. This is one of them. And what we're going to do is take this integral from negative infinity to b f of x dx. It is the limit as t goes to infinity, to negative infinity. Integral from t to b of f of x dx. Let's put this. Okay, let me call this one type 1 part A. Alrighty. So just a moment before we do part B. Right. This time we'll have an integral Okay, we need to just start over. We need for space. Go from a to infinity of f of x dx. This equals the limit as t goes to infinity of the integral from a to t f of x dx. The last type for the first part is to go from negative infinity to positive infinity. Just one more. We don't need a plus sign. Just put infinity. So we'll take the integral from negative infinity to some number c, and then from c to infinity for the other integral, and add them together. Okay, so the first one is the limit. As t goes to, actually, no, we're going to do this. We're going to keep it in integral form, and then you can use the previous parts if you need to. So the integral from negative infinity to c of f of x dx. Add the integral from c to infinity of f of x dx. So for this one, use part A from type 1, and this one use part B. And now we're going to talk about the limits. So if you remember, your limit will converge to a number, or it will diverge to negative infinity or positive infinity, or possibly maybe the limit doesn't exist. But next part is converging and diverging. So I think we're ready. Let's do it. For part A and part B, if the limit exists, then the integral converges. And cool. We'll just, this is an improper integral. Converges. Otherwise, it diverges. So if the limit goes to either positive infinity or negative infinity, then that integral diverges. part C, let's see, we're going to get there in a second. Part C, the integral on the left side, the integral on the left diverges if either of the integrals on the right that you're adding together diverge. So if either of the other parts diverge, it makes the whole thing diverge. All right, part C. Oh no, we're going to go like this. The integral on the left side diverges. If either of the integrals on the right diverges. Okay. And if both of those integrals converge, then the integral on the left side converges. Okay, so I think we need to do type 2. Okay, so we're still talking about improper integrals. And we're trying to type 2. So we're still looking at the integral from a to b of f of x. Dx. And in this situation, see, we integrate from a to b. The function f has an infinite discontinuity in the interval ab. So an infinite discontinuity means there's some number in this interval where the function goes to infinity. Get that in a sec. F approaches infinity somewhere in the interval. In ... continue on. I'll say in the interval of integration. And I think after this, we just do examples. So I'm going to set a timer. Don't want to keep you guys too long. And we're good. First one. We will do the integral from 1 to infinity of 1 over x squared dx. Okay. So before we just jump into using the definition, we're going to do some scratch work and draw a picture. So little piece of the graph of 1 over x squared looks like this. And, oh, okay. Before we keep going though, let's pause because I have a question. Okay, we'll come back to this. So there's a question about converging and diverging. I think I can answer it. Let's do some side. Okay, so you have your integral and change it to a limit, and then your limit. Let's say that we have like a limit as t goes to positive infinity of f of x. If this equals a number, like this equals 2 or pi or negative 20, your function converges to that number. Or let's see, the limit converges. Okay, so in this situation with the indefinite integral, we took the integral, we wrote it as a limit, and if that limit is a number, your integral converges. If the limit is not a number, like something where you have limit t goes to positive infinity of f of x, and get, let's say you get infinity. Then the integral diverges. And then I think the last one is just if your limit is negative infinity, then that one too, and then you got it. Awesome. Okay, and also there's that other piece we talked about, which we'll practice soon, where if one of the pieces diverge, the whole thing diverges. So if anywhere in there you have an infinity sign, this happens. So we had example 1, integral from 1 to infinity, 1 over x squared dx. We started sketching. X values, this. Our function looks like it comes up close to the vertical axis, but doesn't cross. So I have it going like this. On this side. And we're going to start at 1. We're going to talk about going from 1 to some number t. So this down here is some t value. And we'll show you this part here. So we're trying to find areas under curves with these integrals. So we'll call this area A of t. And I'm going to keep doing some scratch work before we do this problem. Cool. So we want to try an integral from 1 to t of 1 over x squared dx. From 1 to t, our function, and what we're going to do is write that as x to a negative 2, and then find the integral, which would be negative 1 over x, and then evaluate from 1 to t. So I'll put that step in here now that we've gotten through our sketch. So what I did is went from here, wrote this interval as 1 to t, x to the negative 2 dx. So you'd have x with negative 2 as your power, add 1 to the power. And divide by negative 1, and then evaluate. I should have just done all of the work in the first place. Sorry, guys. Okay, here we are. Negative sign though. Negative 1 over x from 1 to t. So put in t first and then subtract, putting in 1. And then this is just a piece of the problem, so we're not done yet. Negative 1 over t minus negative 1 over 1. And just want to make sure I got this right. Oh, I'm forgetting my minus sign. That's what's wrong. This is a minus minus. Minus the negative 1 over 1. We'll make this plus. Okay, so this is 1, subtract 1 over t. All right, so what we're going to do is go back to our original problem, write the limit, plug this part in, and then find the limit. Give us the integral from 1 to infinity of 1 over x squared dx. change this to the limit as t goes to infinity of 1 over, no, limit as t goes to infinity of the integral from 1 to t. That's what we need. There, 1 over x dx, and then close this up. 1 over x squared dx. And we did the work for this. So now we've got the limit as t goes to infinity of 1 minus 1 over t. As this number becomes bigger and bigger in the denominator, the value here goes to 0. It gets smaller and smaller. So 1 over big equals small, where that part there approaches 0. So this is 1 minus 0. So yeah, if it's been a little while, what you do here is let t actually go to infinity. That number just sits there, it's right there. As t goes to infinity, this value goes to 0. And you've got an answer of 1. Which means that integral converges to 1. Write that down. I didn't note that it converges, but I just put that when a problem diverges, just state that it diverges and then move on. Okay, any questions? So let's try another one. We're going to have an integral from 0 to 3. Of 1 over z minus 2. dz. Okay, so we'll start some work on the side, and then we'll come back and actually find if we get a number for the integral or if we get that the integral diverges. And finding a number for that integral means that it converges. Let's get used to that part. Okay, so first of all, there's a discontinuity at z equals 2. The function is undefined at that number, so we're going to draw a number line for z values. 0, 1, 2, 3, going from 0 to 3. And there's a problem. This function has a problem, or what's that called? A vertical asymptote at z equals 2. So approach here, there, on the left, and the right. Cool. So I went ahead and just started to split up the integral and work through it, and we'll see what happens. integrate from 0 to 3. We had 1 over z minus 2. Easy. So we'll go from 0 to 2. Integrate from 0 to 2 of the same function, 1 over z minus 2 dz. And then I can draw this picture to the side. It'll help when we talk about the limits, but we need some space. So we got one part, and we need to go from 2 to 3. So add the integral from 2 to 3 of 1 over z minus 2 dz. So we're going to go from this form to the limit form and approach 2 from the left for the first integral. And then we'll approach 2 from the right for the other integral. So from here to there, we take the limit as t goes to 2 from the left. So t approaching 2, and up here we're going to put a minus sign, which means we're going to 2 from the left side. Let's see, we're going from 0 to, let me make sure I get this right, 0 to t? Yes, 0 to t of 1 over z minus 2 dz. Okay, and then add the other integral. For this side, we're approaching 2 from the right. So we add the limit as t goes to 2 from the right. Let's make another variable. We're going to have the limit as u goes to 2 on the right side. So in the exponent, put a plus sign. So we approach 2 from the right of the integral from u to 3. Over z minus 2 dz. So I think we can make it all fit on the board. I'll give you a moment to write everything down, but then I kind of need to start fresh and do the next step. Okay, the next step is to find each of those integrals. So I'm going to leave a bit of this here. The limit as t goes to 2 from the left of is ln absolute value of z minus 2. Evaluate from 0 to t. Those are absolute value bars. Okay. Next part. The limit, we're still adding the limit as u goes to 2 from the right of ln absolute value of z minus 2. And we evaluate from u to 3. So I am going to keep pushing the full problem. The next step, we'll evaluate, put in t, subtract, putting in 0. We'll also evaluate this part. We'll put in 3, and then subtract, putting in u. And then we're probably going to stop and find one of these limits is going to approach infinity or negative infinity. Okay, so next step. And again, I'll use little pieces of what we already have. Let's start a little fresh now. Okay, so we take that part, have it equal to the limit as t goes to 2 from the left of ln absolute value of t minus 2, subtract ln absolute value negative 2. And then there was that other part where we add the limit as u goes to 2 on the right of ln absolute value of 3 minus 2 subtract ln absolute value of u minus 2. So as I mentioned before, if either of those limits diverges, the full thing diverges. So let's just take this part here. So for this piece, let t go to 2 from the left, which makes this value getting closer and closer to 0. As this gets closer and closer to 2, this becomes 0. Take the absolute value and ln. We should sketch this on the side. Okay, so I think I could make it fit on this little corner. So ln, it comes over to that vertical axis, but never crosses x equals 0. And let's see, ln of 1 is equal to 0. So right here, right here. This is approaching 0 inside the absolute value bars. So this is becoming ln of 0. So ln of 0 is equal to negative infinity for the limit. Okay, that's going to ln of 2. Just some number. So we already have this part here telling us that the integral diverges. We'll write that in a second, but I do want to finish a couple of notes before I erase. This would be ln of 1, which we just talked about, is 0. And here again, this is ln of a value approaching 0, and so that function approaches negative infinity. But really, just this part here told us that the integral diverges. So if it were me, I would check out one of the limits, see this part here, and say like, stop. Diverges. 5 minutes. Okay, we'll do more examples next time. So hopefully we'll be able to finish this chapter 7 on Friday. And that's it for today. So